Cauchy sequence. If we write out enough terms, there's going to be some index, some term where after that particular index, all the terms are going to have a difference of whatever we want it to be, less than whatever error we choose. So that is what a Cauchy sequence is, and we're going to write that a little bit more formally here, but that's the general idea. So as you can probably see, the idea of convergence and Cauchy sequence are related, but they're not exactly the same, because for a Cauchy sequence, we don't actually have to care about what the limit actually is, what that number actually converges to, because we're only considering the differences between two terms. But naturally, the results are related, and that's our first part of the proof. We're going to go in this direction today. So if a sequence converges, then it is also Cauchy. It is Cauchy. Okay, so I hope that that is interesting to think about if you are learning this for the first time. Otherwise, I hope that you are nice and comfy and cozy and relaxed. I'm gonna go ahead and tilt the camera down now, and we're gonna write out this definition using some more math notation, and then get going on this little proof. Okay, that you can hear this nice crackly candle now. Let's go ahead and write out the definition. So definition: a sequence, and let's go ahead and just call it A1, A2, A3, dot, 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 so that the first term is A1, so from n equals 1 to infinity. This sequence is defined to be Cauchy. Cauchy is Cauchy if for every epsilon greater than 0, there exists some natural number such that if lowercase m and n are bigger than this natural number, in other words, the am and anth terms are after this a capital N term, after that index, the distance or the absolute value of the difference of the nth and mth term of the sequence is less than epsilon, so within that error. So let's go through this one more time just to break down the notation here. Of course, it's more important to pick up on the logic than it is for all of this notation, but I just wanted to use the most common ones in case you see this in a book or from a teacher or something like that. But this is a sequence, so in our biconvergent example, A1 would be 3, A2 would be 3.1, A3 is the third term, and that would be 3.14, etc. Okay, so that's why I'm writing it like this. I think this is the most clear, but you might see S or SN or whatever. The point is that it's a sequence, and we are defining it to be Cauchy if for every or for all. So I'll just write for every epsilon greater than 0. So for any positive real number, this is going to represent my allowable error or difference between the two terms. So for every epsilon greater than 0, there exists some natural number, some capital N, that's an element of the set of natural numbers, which are just positive counting numbers. So 1, 2, 3, 4, 5, dot, 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 dot. So there is some natural number such that if I have two other indices that are greater than n, so if n is say 5, then m and n would just be any term or any index, so 6, 7, 8, 9, 10, whatever, any two indices that arbitrary, and it doesn't matter if m is larger or n is larger. They're just placeholders. You might see a and b, whatever works for you. But the point is that the difference of the actual n and mth terms are within this epsilon after this particular n. So this works for all epsilon greater than 0. Okay, so I feel like at this point, some people are like, ooh, this is cool to think about, and other people are like, I thought this was math. Where are all the numbers? But I'm hoping that the logic here makes lots of sense to you. So I folded this up so that we can reference it. I'm not going to write directly on this page right now, just because there is a dog that barks outside, and I don't want to ruin the entire sheet. But I'll come back and kind of do some scratch work on it. But let's prove that if a sequence converges, then it is Cauchy. Okay, so let's start with the fact that it converges. So I'm not going to write out the definition of convergence just because I'm about to basically write the same thing. So we're going to review and write the proof at the same time, or at least sketch a proof. I'm not really sure. I don't have this like fully written out. But let's start with the fact that this sequence converges. So let's just suppose our sequence here converges to some limit. That's what converges means, right? In our pi convergent example, it was pi, but let's say it converges to L. So in that example, L equals pi. But here we're just going to say some general value L, since it does converge. And also, let's let some epsilon be greater than 0. So we're given an epsilon, okay? Because we're trying to show that this is true for all epsilon. So let's just give a random epsilon. We're going to keep it general, and as long as we work with everything in general, then it literally is for all epsilon. So if we, at some point we're going to have like an epsilon over 2. So if I give you an epsilon of 1, then the other stuff is going to be 1/2. Or you can pick whatever epsilon if we keep it all in general in terms of epsilon. So that's how we're going to show the for all epsilon part. But the fact that this thing converges means that there exists some natural number. So this is basically the definition of convergent, such that if our index n is bigger than this natural number n is greater than n, so same kind of logic that at some point there's going to be some natural number that's the cutoff for the index, so that all the terms after that nth term are going to be within a particular epsilon away from the limit. So for the convergent case, we're talking about the difference or the distance between terms and the limit. So we're going to start by writing this because it is convergent. So we're given that the sequence is convergent. So therefore this is true. There exists some kind of n, some natural number such that after that we have this thing. Normally I would say that the difference between the term and L is less than epsilon. And that's true in general for all epsilon, but we can also say that it gets arbitrarily close to the limit. And in this particular case, I am actually going to write epsilon over 2. And for right now, it might seem kind of random, but we'll see why that is actually helpful. And if it helps, this is all kind of arbitrarily close anyway. You can let this be like an epsilon naught if that helps you think of it. But when we talk about getting arbitrarily close together, arbitrarily small, this also works. So you can just say epsilon over 2 or epsilon naught over 2. However you want to think about it, it's basically the same thing. We can get as close as we want just noting that this is kind of a sketch part first. So where this comes from though is that I'm going to take a look at this because we're talking about the difference between two terms when we're talking about Cauchy, right? So we want to use this, but then we also want to use the fact that this thing converges, the sequence converges. So I want to use this inequality in this somehow. Well, what I'm going to do is, and this is my favorite part, it's so cute, you subtract this L and then you add it back. So we're doing a little bit of algebra here, and that way we have two parts here, and because they are inside of this absolute value but with the plus here, I can use the triangle inequality to say that that is less than or equal to the absolute value of an minus L and L minus am due to the triangle inequal. So now we know that an minus L is less than epsilon over 2, and where we get this value is that we basically want this an minus am for all. So if n and m are greater than n, so that you can write the same thing for am minus L, because n is just some general index. It might as well be m, doesn't matter. But if n and m are greater than n, then we have this, and we want to show that this is less than epsilon with the same epsilon here because of our definition of Cauchy. So in order to get from this to be less than epsilon, we may as well say that each term is within epsilon over 2, because if this is less than epsilon over 2 and this is less than epsilon over 2, then when you do epsilon over 2 plus epsilon over 2, that's epsilon. So this equals epsilon. So, and also this part would be less than epsilon over 2 because this thing equals the absolute value of am minus L. Okay, because the distance between L and am is the same as the distance between am and L. Or you can think of it as factoring out a negative 1, and the absolute value of negative 1 is positive 1, so that goes away. So this is triangle inequality. So it's up to you how you actually want to write it. I started kind of sketching this in because one thing is that a lot of times when we write out proofs, we kind of want to trace the logic, but we can't just start saying this equals this, because if you go from left to right, that's not quite a correct statement. You can't just say like this equals this, which equals this. It's just that this part equals this, so you might have to break it down into a few more lines there. But this thing definitely equals this, and this is our extra going from left to right, make sure that at all points you're actually making true statements. Otherwise, it doesn't hurt to just take an extra line and restart.